All right, thank you so much, Hussam, for the wonderful introduction, very generous introduction, and I cannot express my gratitude enough about regarding this visit and invite. I'm really looking forward to learning more about your work as well as presenting our work, the wonderful work that my group, my team at Georgia Tech is doing. And we look forward to collaborating with you. I'll be here for the rest of the day. I look forward to talking to you, talking to many of you. All right. So again, Hussam gave a very generous introduction to what we do in our group. So our group focuses mainly on ferroelectric materials, from negative capacitance to embedded memories, main memories, as well as storage. So I'll talk today more about the storage aspects of ferroelectrics. I chose this topic specifically because we hear a lot more about main memory and embedded memory applications of ferroelectrics. So I thought that this topic will be of interest to many of you because it's we hear about other aspects of ferroelectric a lot more. All right. Now, of course, when we give a talk these days, we have to put the AI word in the title, but it actually is a genuine one because you will see that the stock price of the memory companies going up, storage companies going up lately a lot. So this is how it happened, right? A few years back, NVIDIA stocks went up 100x or 1000x. Then I think last year, Micron, SK Hynix, Samsung stock price went up 10x or 100x, depending on when you start. So at some point, people realized that GPUs need a lot of data HBM, right? And then after that, stock price of storage went up because then they realized AI needs not only GPUs and HBM, they also need large amount of data to store. And the greatest embodiment of NAND moving up the memory stack is actually the recent proposal by SanDisk called high bandwidth flash, or the generic term is high bandwidth storage. So for example, on the left, you see a standard GPU configuration where you have the GPU in the middle and the HBM on the sides, right? Now, the proposal that SanDisk came up, I think early months of last year is that you replace some of the HBM with HBF. So if you think about HBM is basically a bunch of DRAM dies stacked on top of each other. I think the latest HBM4 will have 16 high HBM, basically 16 dies stacked on top of each other. High bandwidth flash is a similar concept where you take the flash dies and stack on top of each other. So in that way, you actually have lots more capacity in them. And at the same time, by parallelism, by designing that sub-arrays properly, you can actually have a large bandwidth as well. So this actually quite interesting proposal, and there has been a lot of discussion about what protocols to use for high bandwidth flash or high bandwidth storage to communicate with the GPU and overall mixture of experts, AV cache, all long context windows, all of these things, how to handle it. This is actually a very active discussion right now. Okay, so overall, this is all. I just wanted to set the stage by talking about NAND flash technology and current era of AI, where NAND flash, what the value NAND flash brings in, and what the panel discussions are. Okay, so with that, let me move on. So on your left side, I'm showing the NAND flash storage. It's basically the most common form of flash storage, basically the hard drives that we use, solid state drive that we are familiar with. NAND flash is basically the technology that goes inside it. And over the last decade or so, the density have actually increased 50-fold per decade, which is quite amazing. And most importantly, because NAND flash used to be 2D, and in 2015, it was actually the first semiconductor technology to go truly 3D. So in 2015, it went the 3D route, and density kept on growing. So this is the general 3D view of how the technology looks like at the device level. So at the very core, NAND flash is basically the cell is basically a transistor. So I'll spend a little bit of time explaining what the structure is. This blue pillars that you see, this is actually the channel of the transistor. Okay. So this is the channel over here. So this over here, this my bad. So this gray region is the channel. The blue is more like the pillar. So that mechanically keeps this thing held together. So this blue region is the oxide pillar. This gray region is actually the channel over here. And then this green and the purple region, this is the gate oxide, and this yellow is the gate. So basically you have the gate method, which actually acts as a word line. Then you have the gate oxide, then you have the channel. Why do we call it as a NAND flash? The reason we call it a NAND is because all of these transistors are connected in series. So that's why it's called a NAND. So you can address this transistor over here using this word line, but you cannot actually access the source and drain of this transistor from outside. So that's a key point here. So this is called a NAND flash. And so this is also a non-volatile memory. So that means that the data is actually stored inside this gate stack over here. So I'll talk about the mechanism in it. All right. So another way of showing the same structure, and this is the circuit diagram over here. Okay. All right. So now what has happened over the last couple of last decade or so is quite heroic. The first 3D NAND structure was commercialized, it came to the market in 2014 by Samsung, and it has 24 layers. What does 24 layer mean? 24 layer means that there were 24 transistors of the order of 24 transistors stacked vertically in one column. And it was also called multi-level cell. Multi-level cell means that each of these transistor or each of these cells would hold 2 bits, basically 4 threshold voltage states. And today, in 2022, 8 years later, it went up to like 300 layers. And 2 weeks back at VLSI, Hyungji and Sanix actually reported 1,000 layers of NAND flash using wafer to wafer bonding. Okay. So this has, all these things has happened over the last 10 years, and it's quite amazing how this all panned out. All right. So a couple of things, how we go from 12 layer in 2014 to 1,000 or to 300 layers in 2022. So there are 3 things. First thing is that XY scaling. XY scaling means that each of these transistor footprint from the top actually shrunk, meaning that all these pillars become smaller and smaller. That's number one. So you can fit more of this. And also the die area went up a little bit. Second thing is that when we went from 24 layers to say 300 layers, it's not only that we stacked, the industry stacked more and more layers. These layers, these word lines also come closer to each other. So this is called Z or Z scaling, or Z pitch scaling, or mode height scaling. So basically you need to bring this thing closer together. Otherwise, if you go from 24 layers to say 240 layers, your chip height will be 10x high, which is not something that the package can sustain. And last thing is logical scaling. So we say that in 2014, there were 4 levels or 2 bits. Today, I think we are at TLC or QLC, meaning that triple layer cell or quad level cell, 3 or 4 bits. And there has been also report of 7 bit per cells. That was surprising, but in the market, most of the products are in TLC and QLC. Okay. All right. So now what are the challenges of NAND flash technology? Now we say that last year, in 2 weeks ago, Sandisk and Pure reported 1,000 layers, right? And I say that although I showed that it's tapering off the number of bit area density, it's actually we keep on going for a few more generations. But there are a few challenges, and those challenges are becoming especially important for the AI applications. I'll talk more on the physics side of things, and then at the end probably have some time to discuss why those are important. Okay. All right, so the way the NAND flash actually stores data is the absence or presence of trapped charges in this beta oxide layer. I say CTN. CTN is charge trapped nitride. So basically, electrons or holes get trapped in the gate oxide over here. So if you have electrons or if you have holes, you can say that data stored is 0 or 1. Now, if, as I said, that you actually need to bring these word lines closer to each other. Now, if you bring these two lines closer to each other, what happens is that these trapped charges tend to move or leak out to the neighboring cells. Okay. This is something called lateral charge migration. And this is a key challenge because if this happens, then the distribution of the VT distribution gets widened, and that creates significant challenges when you are actually trying to store terabyte scale data in it. So in other words, you put some data in it, and after some time you see that it's lost. Okay. So that's the first challenge. And this is really a critical challenge. Second thing is that I was actually very surprised to when I started working on NAND flash technology. I was really surprised at how high the voltage is in NAND flash. The voltage of NAND flash is of the order of 20 to 25 volts. It's humongous, right? So on CMOS, we're talking about going to 500 millivolt or 200 or 300 millivolt, right? Here, the voltage is actually 20 to 25 volts. The hard drives that we use, those are probably, if it's a high end, it's probably much higher. Might add, I think it can go to 28 volts as well. Okay, so this is a very high write voltage. And you can clearly understand why this is because, say you want to do QLC. QLC means you have to have 16 VT levels, so 4 bits, so 16 VT levels. So to maintain a certain separation between VTs, you actually need to apply a large voltage. So you cannot, so if I think about 16 levels, 4 bits, if I want to keep like 500 millivolts of gap between them, that means that I need the first VT level and the last VT level, I need to maintain at least 8 volts. Okay? So to get to an 8-volt memory window, you need to apply 25 volts, as simple as that. So that's basically the problem statement. Now, this high voltage creates a lot of challenges. First thing is the reliability challenge. If you have a QLC NAND flash, you cannot actually write it more than 10,000 times. So reliability is a key challenge. Second thing is, say you apply 25 volts in one word line and another one is at 0 volts, then this is a large electric field across them. So the reliability of this interlayer dielectric is also becomes poor. So high write voltage is a key challenge. And then, of course, if things become closer, the coupling becomes a big challenge. It gives a lot of disturb. And finally, when things get smaller, variability becomes a key challenge. So all the standard problems that we know that happens in any memory technology or any semiconductor technology for high voltage, the same thing plays out in NAND flash. Now, these are the challenges. Okay. So actually, we started working on this project around 4 years back, and we worked very closely with Samsung on this project. And the main idea was this, that we started thinking about in terms of lateral charge migration. So the reason I mentioned lateral charge migration happens is because these are trapped charges and they can move to the neighboring worlds. What if we change the mechanism to something else where it's not happening with a trapped charge, rather it's happening with something that has a bound charge? I'll explain the concept of bound charge, but basically the idea was to use something that uses bound charge in terms of trapped charge. And of course, ferroelectrics comes from a bound charge. So we wanted to see if that is possible. All right. So ferroelectricity, I think we don't need to give an introduction to ferroelectric studies proud here, but for the sake of completeness, I'll just mention it. Ferroelectricity is a phenomenon that happens in crystalline materials. Basically, the the charged ions are not at the center of symmetry of the crystal structure, but rather slightly off-centered. And the most important thing is that this off-centering can be changed by applying an electric field larger than the coercive field. So basically, if I have a ferroelectric material and sandwich between two metals, I will get registers in the charge voltage characteristics, and it will work as a non-volatile magnet. Okay. So I'll just now explain how we think about ferroelectric field effect transistor for NAND flash applications. I will use a little bit different kind of a schematic diagram, different from what we usually use to explain a ferroelectric field effect transistor, because I really want to make a comparison between standard charge trap flash and a ferroelectric flash. Okay, so on the left, we have a NAND flash structure, vertical. This white region is the channel. This is the gate stack. So the NAND flash has a gate stack of a bottom oxide, top oxide, and a charge trap nitride layer. And if there are electrons trapped here, then we store some data, 0 or 1, and that happens when we apply program calls. So now if I have electrons trapped over here, then my device will have a larger threshold voltage. Now, okay, so if I now apply a positive voltage on this one, polarization will be pointing to the channel over here. And when the polarization is pointing towards that way,
is the button of the clicker hanging?
I think it is getting some interference from the other electrical things, maybe.
Yeah, someone hacking track your talk.
All right. So when the polarization is pointing to this side, we have positive charge like this interface, and as a result, they'll have more electrons over here, so that the threshold voltage will be negative. Okay. Now the next thing is, let's say now we apply a negative voltage over there, so there will be no electrons here, and as a result, I'll have a negative lower threshold voltage over here. And if I apply negative voltage here, the polarization will be pointing to the other way. And as a result, I'll have a larger threshold voltage. Okay. And what do we call the gap between these two curves? The basically difference between the threshold voltage is the memory window of the device. Okay. Now, one of the important thing to understand here is that, this is for general knowledge, that when we apply program pulse, which is a positive voltage, the threshold voltage of a NAND flash is actually high. And when we apply positive voltage, positive voltage to the ferroelectric, the threshold voltage is actually low. So it's an opposite programming.
If you prefer, you can put the laptop close to you. Exactly.
All right. Okay. So now let's go into the numbers that we want to hit. So it's an engineering problem, so we cannot just do basic physics. So we need to have some design parameters. So if I think about a ferroelectric NAND flash, we have approximately 100 nanometer of budget for the entire structure, because we need to fill the trench. And in the trench, diameter is of the order of 100 nanometers. Now the oxide filler is around 50 to 60 nanometers. The channel is approximately 10 or some around 10 nanometers. So that really leaves us a gate stack thickness of 20 nanometers. Okay. So the ferroelectric gate stack has to be around 20 nanometers. It cannot be more than that. On the other hand, for TLC or QLC applications, the memory window needs to be of the order of 6 volts for TLC and 7.5 volts for QLC applications. Where does it come from? It comes from the fact that we need to have a certain amount of gap between each threshold voltage state. Otherwise, we won't be able to distinguish them, considering how tight these distributions are. And finally, as I said, today's NAND flash works at 20 volts. We want 15 volts to be the right voltage for NAND flash. Why 15 volts? I mean, even if we can get to 18 volts, it's great. But the thing is that once we want to introduce a new material system into the entire stack, it better be so much better than what we have already. So 15 volts was our initial target.
And you need the positive, negative.
Then positive 15 and negative 15.
How much this is problematic in reality? Because whenever you want a negative voltage, it's a big problem for any circuit.
Yeah, so that's a awesome point.
Because we designed the circuit.
Right. Yeah, I mean, I know, and my colleagues in digital world say that they even don't want to generate different voltage levels, right, on the digital world. So yeah, that's a great point. And the NAND world, I'll give you a little bit of sense of how things are in NAND world. I myself is not a circuit person, but I get these questions. So yeah, first thing is that it has to be positive and negative. Okay. And then the thing is, say I want to move it to say threshold voltage to this value. You know how it goes there. So it's actually steps. It's something called incremental step programming, ICE programming pulse, ISPP and ISPE. So I don't remember exactly what it stands for, but it's ISPP and ISPP. PE. So basically you apply a voltage, you set the maybe here. Then you apply another pulse, so it moves here. Then you apply a smaller pulse, then it moves here and there. This and every time, so say you want to put it here. Every time you do it, every time you apply a pulse, you need to do a read verification. So eventually what happens is that every time you want to perform a write operation, it takes of the order of milliseconds. And it's not that you can just arbitrarily put it here. You have to go by steps. So it's extremely slow, of the order of milliseconds. So if you're coming from logic board, milliseconds is the end of the world, right? But this is a different world. Okay. But that being said, for AI applications, you cannot sustain 1 millisecond, right? Especially what we're talking about, that if you want to use it for move it up the memory hierarchy, right? Or closer to the HBM. So what happens is that this QLC and TLC is very interesting for pure storage applications. But if you want to use it as a high bandwidth storage or high bandwidth flash, it's better to use it as SLC, like single bit memory, because then you can read and write very quickly. So yeah, so that's what it is. Now, there are already applications of, so QLC is for dense storage, right? Or laptop or anything. But if you think about high speed applications like if you go work, right, you have high speed cameras. I was told that those high speed cameras actually use 1 bit NAND flash because there needs to be faster. Okay. But another thing that I also hear is that SLC, TLC, QLC, all are actually the same chip. So basically the QLC chip, you also can use it as an SLC mode. But in doing so, you cannot actually reduce the voltage significantly lower than 20 volts because the stack design is the same. So irrespective of whether using SLC or QLC, your write voltage will remain almost the same. Okay. The latency will be the same. Okay, but nonetheless, these are the parameters that we have. Okay, so now before I get into the details, another thing is that what is the maximum limit of memory window that you can get out of a ferroelectric field effect transistor? The key thing here is that we want 7 or 6 volts of memory window with 20 volts or 20 nanometers of ferroelectric thickness. Now, for a long time, it has been known that the maximum memory window that you can get out of a ferroelectric field effect transistor is 2 times the coercive field times the thickness. Now, if you look at the coercive field of hafnium-based ferroelectrics, it's 1 megavolt per centimeter. So multiplied with 20 nanometer, you get 2 volts. So if you have 20 nanometer of ferroelectric thickness, you will actually at best get to 2 volts of memory windows. Okay. So that's why it was not as straightforward to think about ferroelectric as a drop-in replacement for NAND flash. So just plotting the same curves over here, same thing. So if we looked at the literature back in 2023, gate stack thickness on the x-axis, memory window, and you can see that most of the data points that you have there actually lies on this line over here. Where do you want to get to? We want to get to somewhere here, but if you use a pure ferroelectric, you cannot actually get to that 6.4 volt memory window line. Okay. So then what we did is we tried to look into how we can design the gate stack. So we took a 19 nanometer hafnium zirconium oxide layer, plotted the right voltage in x-axis memory window, and you can see that as we increase the right voltage, the memory window does indeed go up, but it go up to 3 volts and then it doesn't go up anymore. We want 6 volts, 6.5 volts. Okay. So then what we did was, at that time, my postdoc, Dipjyoti Dash, he inserted 1 nanometer layer. So remember that our total thickness budget is 19 nanometers. So we inserted 1 nanometer and reduced the ACO thickness a little bit. So 9 plus 9 plus 1 is 19 nanometers. So basically the total stack thickness remains 19 nanometers. And then what we could clearly see is that as we insert 1 nanometer of aluminum oxide, the maximum memory window actually jumps up by almost 60% to around like 5.5 volts. So we are very happy. So that by adding 1 nanometer aluminum oxide here, we could increase the memory window significantly. Okay, but even then, we are not reaching the 6.5 volt limit. So, but we already got the idea that if we put an aluminum layer, we can enlarge the memory window significantly.
May I ask, how did you get this idea?
So, this idea, so.
It's a very good question.
Right, so, we always stand on the shoulders of giants. So my giant was my postdoc.
But in the world of FE-FET, I remember some people, I don't know, Suman and others 5 years ago or 4 years ago, they started also to really play with the stack. And I forgot what was the physics behind that. Is it the defects? Is it the I think the field distribution? Maybe you can comment on that.
Right. So one of the so that comes from the world of negative capacitance. So and what we actually did, so the idea was that we put HCO thin layer of HCO, thin like a dielectric, another HCO, or like to hafnium oxide, zirconium oxide, very thin layers of it. So that we call nano laminates. So basically, you can take a very thin layer of zirconium oxide, which is put on ferroelectric or an anti-ferroelectric. Put a non-ferroelectric layer like hafnium oxide or alumina, and each of these layers are of the order of less than a nanometer. That's the term that we use generally, superlattice or nano laminates. So, and that was more for the logic applications.
I have a small question. Is this a process assumption or it's already fabricated?
Fabricated.
Oh, yeah, these are fabricated devices. Yes. So, yeah, so to answer your question, yeah, there is precedence. Like, actually, my first negative capacitance paper back in 2011 was something where we used ferroelectric and dielectric stack layers. So, and then all the ideas that came afterwards on negative capacitance were basically layering the ferroelectric and non-ferroelectric together. So this is a similar idea, but actually the physics that works out is completely different. We'll show in a bit. But yeah, to answer your question, it was the magic of my postdoc.
So I need to find better postdocs. No, they are doing great, but they are not doing magic.
So yeah, I mean, this was quite interesting. So this was actually published in IBM in 2023. It's a highlight paper. Okay, so to answer your question, we do go into the details of the defects, but I also want to finish up very quickly. So how much time we have? We have around 15 minutes.
Informally. So,
okay, cool. All right. Okay. So then my postdoc, Dipjyoti, increased the aluminum oxide layers. Now it looks very simple, but it's just seemed like that as we increase the aluminum oxide thickness, the maximum memory window actually goes up. almost linearly.
So just to make sure you cycle the device and the window is stable. It's not like, just not artifact or temporal effect from the traps or those things. So you keep cycling and the window is stable to.
So I'll show some of the results in the later slides, but the answer is yes and no. This is one of the key challenges of ferroelectric field effect transistors, endurance cycles. So if you are in embedded memories, you need to go to 10 power 16 cycles or something like that if you want to do something like SRAM. If your memory 10 power 16 cycles, like main memory, like 10 power 16 cycles. For NAND flash, the thing is if you are in QLC domain, you want at least 10,000 cycles of write endurance. If you're in SLC, you want 10 power 8 cycles or 10 power 8, above 10 power 8 cycles. So the key metric is for QLC applications, 10,000 cycles, which is 10 power 5 cycles. Now, what we can see is that in our best case scenario, we can go to 80,000 cycles. So reliability is a Prof challenge, which I think among all for ferroelectric field effect transistors, for NAND application, it's looking more promising, the reliability.
For SLC.
For SLC, no, for QLC. For SLC, you need to be much higher. Okay. So I'll actually show some of the benchmarks there in the later slides.
So 80,000 is for QLC.
Yeah, 80,000. 80,000 is what we are getting. And for 80,000, the minimum number that we get is 10 power 5. So, yeah, so we'll talk about it. Maybe. Yeah. All right. So 1, 2, 3, we can clearly see that we can actually, it's a design variable, how much aluminum oxide we put, and it goes up. Right.
A question just about the graph. So it seems that at lower voltages, you're losing some memory window, and then it's kind of like spikes like as you approach a higher voltage. Wouldn't that be a problem to the right scheme user adapted where you do lateral increase of voltage?
Right. So there is this ISPP slope or ISPE slope, which is related to the slope of this curve. So one thing is that you don't want a characteristics like blue or this color is what purple. These two colors. The reason is that these two will be very much sensitive to disturb effects. So you actually want something that rises sharp and then stays constant. So that's what you need for disturb. So yeah, that's a very good point. Yeah, so we actually wrote a bunch of paper on the disturb as well. So we'll show you a little bit of it. All right. Okay. So now these three stacks, we initially wrote this theoretical curve over here, and these are the three dots that we are showing that using this structure, we can actually exceed this fundamental limit. So we'll talk more about how we are achieving this fundamental limit. So we are going above the 2-volt limit for ferroelectric field effect transistor by putting in this dielectric layer in the middle, and we are calling it a tunnel dielectric layer. Okay, so that was the first work that we did in 2023, and after that, two of my students, this one is Lance Fernandez, did a series of studies of doing various designs of this gate stack. For example, in this case, you see a green and a blue. So the green is the green layer over here is aluminum oxide, and for this yellow is silicon dioxide. So you can take many dielectric materials and mix and match with ferroelectric. It's truly a large design space, and you can show that you can actually exceed this fundamental limit of 2 volts by a large margin. So, for example, in this case, we are reaching 10 volts of memory limit with this structure where we have 6 nanometer is 2 nanometer of aluminum, 6 nanometer is 4 nanometer of silicon dioxide. And then he also went more crazier because then he introduced 2 more materials, silicon nitride, and I think hafnium oxide, all these things, mix and match, you can get a long variety of different things.
Do you do TCAD simulations or just go to the clean room and whatever comes to his mind start?
Yes, yeah, I mean, Lance has been being creative and on his own. So it's only after he publishes the paper I get to understand what he's doing. So yeah, so he's doing all these things on his own, and I don't know how many papers he has so far published, but he has published a lot of these things. Yeah. So it's mainly experiment driven. The reason is that these experiments, and because of France's expertise, it's much easier for him to do the experiments than doing the simulations. Understanding these stacks is actually, we're in the beginning phase of understanding where this memory window comes in. And the reason we want to understand where this memory window understand, because this has significant implications for reliability. So that's very important for us. So the TCAD aspects, we have done some of it, but there are a lot more to do. Okay.
Can this even be reasonably simulated with TCAD? Because with all of these complex interactions and the complex gateways,
There should be more, or what's called these atomic simulators from synopsis should be more material.
Okay.
Right?
Yeah, so we do a lot of this. We work very closely with the Genestra team, and we have been doing a lot of simulations. But at the same time, for example, the temperature dependence, voltage dependence, all these things, as well as we're doing a lot of material characterization, starting with XPS, EDS. And then we are doing some scanning tunneling microscopy experiments to see where this memory window enhancement comes in. I'll show 2 slides on where we think this memory window enhancement is coming, because that's important for the reliability aspects. All right, so we started this work 2022, and by 2024, we get all these data points showing that we can actually massively expand beyond the memory window limit of ferroelectric field effect transistors. And I'm so glad, because we are not the only ones. There has been, since 2023, there has been a lot of papers on these things from the major memory makers, for example, SK Hynix, Micron, Samsung. All of them have shown different aspects of this ferroelectric field effect transistor for NAND applications. So this is a very exciting field now. All right. And then this is not only us, there are so many groups across the world who has been doing it. So this slide, this box is our results, basically Lance's work. But then there are so many other groups across the world doing different aspects. And truly, this is 20 nanometer stack, and you have entire periodic table to make all these gate dielectrics and so on and so forth. So it's an exponential design space. So the experiments, you can be very creative and come up with very good things. And there is a need for being creative here, because what I showed is only the memory window so far, but there are other reliability challenges which I'll be talking about in the next slide. Okay. So in the previous slide, I only have put our own data, but now this slide shows x-axis gate stack thickness, y-axis memory window, and everyone else's data. And you can clearly see that how the fundamental memory window limit has been exceeded in this case. All right. Okay. So I'll quickly go over why we think where this memory window enhancement is coming from. So if I think about it, so if I have a ferroelectric field effect transistor, this is a standard ferroelectric field effect transistor where we have just an H0, but here what you have is H0, but there are another dielectric material. Now, if you think about it, what is the main difference between this? The main difference between these 2 structures is the 2 additional interface that we get by putting in the dielectric layer in between. And whenever there is an interface, there are extra defects that we have here. So we did a simple coupled Schrodinger's coupled Poisson equation coupled with price of model of ferroelectric, simple model, where we also introduced the interface traps. Okay. So what I'd like to first show is that there are 3 plots that I'm showing with different assumptions of traps. So first thing is that if we don't have traps any of these interfaces, like if I don't have traps here or here or here, then you will see this kind of a trend where the right voltage memory window, and you can see that the 19 actually is supposed to have the largest amount of memory window, then 1 nanometer alumina and 3 nanometer alumina. So it does not match with any of the things that we are seeing in the experiment, because in the experiment we are seeing that 3 nanometer alumina has the largest amount of memory window. So that's what we see. Okay. So the next one is that we then introduce that, okay, maybe the traps over here are 0, but we still have traps over here. And in that case, we get a better prediction or better simulation results, meaning that all the memory window, maximum memory windows are of similar characteristics. And importantly, we see that there is a peak memory window and then it goes down. Okay. So we see that characteristics, but still quantitatively, it is not picking up the experimental trend that pure HCO has is like when you have 3 nanometer alumina that has the maximum memory window, but still this case does not simulate that. In the last case, what we did is we introduced traps at all the interfaces. And then actually we very clearly see that the experimental trend is captured here, meaning that when we put the aluminum oxide, there is a massive enhancement of the memory window. So I'll actually not talk more about the simulation in this presentation anymore, but if you want to learn more, we'll actually be very happy to share with you what the underlying assumptions were. Now, I think that underlying assumptions were not were reasonable. All of these cases, we had like 15 parameters. Okay, whenever we do a simulation with 15 or 20 parameters, you can fit anything. But the reason I tend to believe that simulation is because in all cases, all the parameters were the same except only one parameter, the strap density was changed. Okay, so this basically kind of shows we think that the addition of the memory window that is coming because of the defects or charge traps that we have at those interfaces. So I'll quickly go over the comparison. First one is that traditional NAND flash has a large memory window, comes at the expense of large write voltage, and the mechanism is trapping. In case of conventional ferroelectric field effect transistor, the good thing is it's a low write voltage, but the memory window is also low. And the memory window mechanism is polarizing switching. Now, in our case, we are putting an aluminum oxide layer in the middle or a dielectric layer in the middle. We get a moderate write voltage, but get a large memory window. So this is the best of the both worlds because we can reduce the write voltage from that of the NAND flash by getting a large memory window.
Doesn't this reintroduce the problem of leakage again?
Yes, that's a very good point, right? So that's what I'm going to talk about. So you're saying that, okay, we have polarization, switching, trapping, and tunneling, all three of these. Now, what you're saying is that main problem of NAND flash was trapped charge at those layers, and those were leaking out to the sides. When we started, we saying that ferroelectric is a bound charge, not trapped charge, so it will have less lateral charge migration. But then we are saying that we are getting a 50% increase of the memory, like we are exceeding the fundamental limit of because of trapped charges. So are we back to square one? We don't have yet the experimental result to prove or disprove that. But the main thing is that in case of NAND flash, the trapped charges are trapped within a bulk. Here, the trapped charges are at the interface. So the amount of space that they have to move is much smaller, and also they're bound by the polarization. So we think that there will be lateral charge migration effects in ferroelectric. We call it the band engineer ferroelectric field effect transistor. There will be lateral charge migration, but to a much lesser extent than that in flash because those trapped charges are truly at the interface. And second thing is the voltage is much less here, 25 volts versus 15. So the charge trap, lateral charge migration will be much less. But of course, this is then I'm very excited to see what we see in terms of lateral charge migration because we're working on that right now to really scale devices and see how the charge trap increases. It's a fundamental problem because we still don't understand fully where this memory window enhancement is coming. If we understand, we can solve all these problems. Okay. So now in the next 7 minutes, I'll give you a quick scorecard of ferroelectric field effect transistor in terms of the reliability metrics. So we already talked about write voltage and memory window, but we'll talk also 3 things: retention, disturb, write interference, and scalability. So we actually publish all this work. If you want to understand more, there is this paper which you can actually look at. It has all the summary of all that work that we have done. Okay, so the first thing that we did was retention. So in the case of retention, I'll quickly go to the next slide. We took 3 different devices. One is the pure ferroelectric, then one with aluminum oxide in the middle, and then silicon dioxide in the top. Okay. So in both cases, the main thing is that both of these devices actually show very large memory window. But what is quite interesting is that if I put the layer over here, both aluminum oxide or silicon dioxide, what happens is that it actually shows quite large memory window at the beginning, but the retention is poor, meaning that you can see it goes down. And if you go to 125C, why 125C? 125C or 115C is more like a higher temperature limit where any device, any chip needs to be qualified for a certain amount of time. So when you put the dielectric layer on top, you can actually see that the memory window goes down significantly and the retention is poor. But when we put the aluminum oxide in the middle, you can actually see that the retention actually stays within 10^4 seconds. There is no loss of memory window at room temperature, and even high temperature is much less. So bottom line is that although the memory window can be increased by putting the dielectric layer in the middle or on the top, but depending on where you put the dielectric layer actually controls the retention properties. So that was not obvious from the memory window characteristics, but it's obvious from the retention. So now this is not our work, other people's work, but just to give you a sense of what all the exciting work is happening. So what people have found is that if you put a single layer on top, so in the previous slide I showed that if you put a layer on top, you actually get very poor retention. But then other groups have shown that if you just put two dielectric layers on top or multiple layers on top, then you actually get very nice retention as well. So putting in the top, retention is poor, memory window is high, but if you put multiple layers on top, then retention goes down. So there are a lot of interesting physics going on there. Okay, so then the matter of disturb, and this is actually quite interesting and exciting because I think that Hussam and I were talking, right? So there are actually interesting things that can be done to disturb effects that we can probably work together, come up with circuit techniques to implement the ideas that I'm showing you. Okay, so I'm sure that you are all very familiar with disturb, and the main thing is that, say, this is my target cell. And if you do a program here, it can be affecting here. If you program a cell over here, it will affect here. Or if you want to read this device, or if you want to read this device, this might get affected. So there are read disturb, path disturb, and write disturb. So what we saw is that if you take a structure like this and apply read pulses, then you actually get threshold voltage continuously shift to the right. So there are details over here, but what we are actually showing is that we are applying 50 microsecond pulses. In NAND board, these numbers are actually microseconds. So we are applying microsecond pulses. These are the disturb pulses. So this is the initial state, and if I apply 10^7 read cycles, you can see how the threshold voltage is shifting here.
But what is the read voltage here?
So the read voltage is the way we are measuring it is just tracking the threshold voltage. So threshold voltage means that we are actually measuring.
No, sorry, what is the read? How much voltage you are applying during the read?
Right. So okay. So we are applying VT plus 2 volts. So VT plus 2 volts means that we are here. So we are applying something around here, like 1.5 volts.
Okay, and 1.5 will definitely cause disturb, right?
It is causing in this case.
Yes.
Okay, it is causing this case.
But I mean, I said, what's the reason to go to relatively high read voltage? Why not 1.2 or 1.1, which is safe and will not cause any read disturbance?
Right. So the thing is this, right? So remember, this is a NAND structure, right? So to be able to program something in here, right?
Mm-hmm.
You actually need all these transistors to be conducting.
Mm-hmm.
So as a result, you need to apply certain voltage over here so that it turns on. Because you don't have connections from outside to this. So all these devices has to be turned on.
Okay, you need the channel, but you need to go to the 1.5.
Yep. Right. So that's the key challenge there. So right. And once you, so this is the pulse resistor, and when you do it, you can clearly see the threshold voltage is dramatically. The other thing is that it's moving to the right, so it means that it's actually not due to the polarization switching. It's happening because of electron trapping in this interface over here. Okay. And if you can see that the threshold voltage actually increased significantly, I think around 24% increase in the threshold voltage, basically from 4. Now, when we talk to our colleagues in the industry, they actually, this happens to some extent in standard NAND cells, especially when you have cycled it a couple of times. So in the NAND controller, there is a mitigation pulse technique, meaning that after a certain number of read pulses you have applied, you apply a mitigation pulse in the negative direction. So what it does is that there are electrons that are trapped during these pulses, and if you apply negative pulse, then all these electrons actually get flushed out. So it goes back to original. So we also did a similar disturb mitigation scheme where in the previous case, we were applying all these pulses, but now what we're doing is that we are applying a negative pulse over here. Okay. And once we do that, we can clearly see that previously without any mitigation, there was 28% disturb, but now once we have this mitigation pulse after 80,000 cycles, it goes down to 16. And in the extreme case, just for the sake of demonstration, if we actually have a mitigation pulse smaller, then we can actually reduce the disturb to 4%. So there are actually, the point of this slide is that there are very interesting ways of doing clever things to make things work. And so I have been following the work of Robert Noyes and other leaders in semiconductors in early 60s, 50s, right? Things were always like this, that early MOS technology was very unreliable, but they always found very curious way of solving this problem, interesting, clever ways. I think with Ferroelectric, we're at that stage that we are actually figuring out many different things, many mechanisms, and ultimately, whether it becomes a widely used technology or not, I don't know, but there are a lot of interesting things that can be done. And things actually happen when a device or technology group like ours work with someone circuit system group like yours. I think that's the most exciting part.
Yes. So here, when you're mentioning disturbance, you're meaning disturbance on the cell you're reading, because a specific transistor you're reading, right? What about the other ones in the same column that are also getting activated so that you can read this, which will also get disturbed, and there you cannot do this mitigation because you don't know their state. So your mitigation might somehow remove the state.
Right. So we just need to do it blindly, meaning that we would assume that all of these things will happen. And if there is a self-limiting thing to it, meaning that some device will move to this red curve, some to a yellow curve, some to the blue curve. Yeah. The self-mitigation thing is that if it's blue, it will back to back. If it's red, it will still move to back, and it will move to back. So that's needs to be happening. Like that's what I think happens, because once your electrons are flushed out, you are not getting any more electron out of the system. Only way it will move past this if we actually start trapping holes. The barrier of holes is much larger, so it won't move to the right. So yeah. Okay. All right. So yeah. So this is the second part. Pass disturb. Okay. Now the last part is the endurance, and this is the one which we're discussing. How much endurance cycles we need for NAND flash technology? For SLC, we need of the order of 10^8. And these are the different nodes, 1x, 2x, 3x, 5x. And for QLC, I think we need to go up to so this scale is probably not showing the right numbers on the y-axis, but for QLC, you have to be on the 10^5 cycle region. Now, if you look at this diagram over here, y-axis is the write endurance, x-axis is the memory window. One clear trend you see is that if you are at the lower end of the memory window, you can actually reach 10^11 cycles or 10^10 cycles of write endurance. But if you're on the lower end of the memory window, you actually need to reach much higher endurance. On this side, where you have of the order of 10 volts or 15 volts of memory window, we get around 10.4 cycles or 80,000 cycles, or if we stretch, we'll get 10 power 5 cycles over here. Here, so the bottom line is that as you increase the memory window, the endurance that we get goes down. But quite interesting that these data points are actually much closer to the what we need for an technology than these data points, because for embedded you need much higher write endurance. But here you actually need to go 1 or 2 orders of magnitude. Okay. And I'll not go into the details, but the mechanism for breakdown for a standard ferroelectric field effect transistor versus one where we have a dielectric in between with large memory window is actually different. In this case, what standard breakdowns is the IL. In this case, what we think breaks down first is the ferroelectric, not the IL. Okay. So this is what we think. Happy to discuss more. Yeah, so that's that. So overall in the 6 matrix, these 3 are more or less under control, I think. Right, endurance is something that we are working on. And scalability and variation is something that we already discussed that. Our initial idea was that we don't use trap charges, rather ferroelectric bound charge. It should be better, but we are actually using trap charge to increase the memory window. But we think that the lateral charge migration will be much less because these are basically interface terms. Okay, I'll finish off my talk with something that we see a lot these days on the news, because our friend Elon Musk wants to build data centers in AI in the space, right? But it's actually something very important because by no means space is an important part of our AI infrastructure right now. There's no question about it. So now I was very surprised to see that today's NAND flash technology is very sensitive to radiation. For example, if I take a standard NAND flash, it actually can sustain up to 50 kilorats of TID, total ionization damage. So now if you think about it, what is 50 kilorad? If you think low Earth orbit satellites, they 5 to 30 kilorad, or these have for geo missions, you need 100 to 300 kilorads. And if you think about deep space missions, you need 1 megarads of radiation. Now, if you think about putting a lot of AI capabilities in space or orbital AI infrastructures, you cannot put magnetic hard drives there. So magnetic hard drives are very known to be very radiation tolerant, because magnetic materials don't interact with radiation. But you cannot put magnetic storage in space a lot because of the weight, number one, and also its mechanical sensitivity. So I was quite surprised that there are no good solutions to storing massive amount of data in space applications. So what we did is Lance then took one of his wafers and sent it to Penn State for radiation studies. And what we actually could find is that our devices actually remains very stable even after 1 megahertz of TID. This is actually 30 times lower sensitivity to what traditional NAND flash technology has. So this is another direction that we're going into, ferroelectric NAND flash for rad-hard applications. So this is just an initial study, but we have to do more studies on single event offsets and other aspects of radiation. But this is quite exciting. And the reason ferroelectrics are in general known to be radiation tolerant, but for NAND applications, this is we are the this paper actually showed first time the radiation hardness of ferroelectric NAND devices. All right, so I'll finish up my talk with two more slides. One is summarizing all that is going on in NAND. First one is that NAND is moving up the memory tier, and ferroelectric is, we think that will be an important player in that space. I did not talk about this at all, but computing memory, basically doing computing in memory with the NAND structure itself is quite an interesting area. We work with some of our collaborators in India, Professor Tanner Rosing, and there we are looking into how we can actually process very large data sets that come from proteomics or genomics, those kind of things, and how we can use ferroelectric NAND for those applications. That's quite interesting aspect of it, which I did not talk about. And lastly, the random storage. Okay, so with that, I think that NAND will be an interesting area to work on for AI applications, and ferroelectric will have a very strong place in there. I really wanted to add this one because all of the talks that we do in our group, we all put it in the our YouTube channel. So this video will also go to the YouTube. Last but not the least, I must give credit where it's due. All the work that I showed here was done by my team at Georgia Tech. Especially most of the work I showed was done by Lance, and the initial work on NAND was started by Bigjyoti over here, and our work has been generously sponsored by Samsung Electronics, Semiconductor Research Corporation, 3D Fem 2, which is a DOE center. All right. So with that, this sample Atlanta, this is actually how Georgia Tech looks. I told so. Hussam actually mentioned how beautiful Munich is. And yesterday we spent a lot of time across historic part as well as the new part of Munich. So I thought that I'm going to add this slide so that you all come.
Where is your office?
So yes, I'm going to talk about it. So my office is somewhere over here.
Okay.
And most of my students are in the clean room somewhere over here. And when they're outside of the clean room, they go to the other side. Now, this is interesting because this is a financial district as well as arts and culture district. So yeah, so that's what it is. And even now 2 years back, I think 30 to 40% of all Hollywood movies were made in like that in Georgia, great state of Georgia. And when I moved there 10 years ago, gosh, it has been 10 years ago. We saw that for one of the Marvel movies, one of the street workers. So come here, you might end up in one of the Marvel movies there. But yeah, so come visit us at Georgia Tech.
Thank you. Yeah, many thanks. Great, full stack. You have questions?